So let's jump into it. This first example asks us to find the power series for a particular function, f of x equals e to the x. So in these sorts of problems where we're given the value to which the series converges, in other words, e to the x is the value to which the series is supposed to converge, then it's going to be a Taylor polynomial. Or in this case, perhaps a, well, it doesn't specify, does it? We could use Taylor polynomial centered at 1 or 2 or any other x value. But let's pick x equals 0. Let's make this a Maclaurin polynomial because that's the easiest one to do. And we've done this a number of times already, so I'll just blast through this. We've got f of x equals f prime of x equals ... equals e to the x, right? So that means that f of 0 equals f prime of 0 equals 1. All of the derivatives equal 1. So that means that f of x equals 1 plus 1x plus 1x squared over 2 factorial plus 1x cubed over 3 factorial. That coefficient in the numerator is always 1. And I'm going to keep on going. And one nice thing that you can do here, if you can figure out the pattern, if you can figure out that nth term happens to be in the form, in this case, it looks like the exponent and the denominator have that same number. So I'm just going to raise x to the n, and I'm going to put n factorial on the bottom. And that's going to give me a degree n Taylor polynomial for e to the x. That's not what we want, though. We want a series, so we want it to keep on going. So I'm actually going to put a very, very important plus ... there. Don't forget that this thing is continuing on forever. So a common question might be, find the first 3 terms and the general term of the Taylor polynomial, or Taylor series. This is the first 3 terms, first 3 non-zero terms, and this is the nth term, or the general term. The reason we like the general term is because we can now write this f of x as the sum from n equals 0 to infinity of x to the n over n factorial. And remember that f of x equals e to the x, and we have just found that e to the x can be expressed as that infinite sum. Let's get rid of that. But for what values? It says then to find the interval of convergence. In other words, the question is, does this thing converge to e to the x for every value of x, or does it just converge to x for some values of x? So let's give this a try by using the ratio test. The ratio test asks us to find the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. In this case, we've got the limit as n approaches infinity. Let's see, we've got x to the n plus 1 divided by n plus 1 factorial divided by x to the n over n factorial, so multiplied by that reciprocal. These should look familiar from our last unit. And exponentials and factorials are very nice for the ratio test. Everything cancels out except for the x in the numerator and n plus 1 in the denominator. Now, when you look at this limit, you might get a little confused. You're saying, well, wait a second, I don't know. It depends on x. It depends on n. Well, let's consider this. The limit is only asking what happens as n goes to infinity. So we have to ask the question, what values of x will affect the limit as n goes to infinity? So I'm going to pick a value for x, let's say 1, and I'm going to let n go to infinity. And if I have 1 over 2, 1 over 3, 1 over 4, 1 over 5, we all know that sequence heads off to 0, right? Dividing by bigger and bigger numbers puts us to 0. But if I picked a different value of x, say 10, would I get a different behavior? Well, 10 over 1, 10 over 2, 10 over 3, well, that doesn't get close to 0 quite yet, but if I do 10 over 10, 10 over 100, 10 over 1,000, then you're going to see that if we keep the numerator fixed at any particular value, and we allow that denominator to grow, then no matter what value of x we pick, we are going to see that this limit equals 0. Okay, so x is not the variable in this limit, n is the variable in this limit. For every value of x we pick, as n goes to infinity and x stays put, we're going to get a limit equal to 0. And the important thing here, of course, is that the limit is less than 1. Therefore, let's put that in this blank space over here. Therefore, the series converges for all values of x. This is exciting because that tells us that we can plug in any value of x we would like to into this equation, and we let that series go to infinity, and that value will converge to e to the x. Okay, so the radius of convergence in this case, does anyone know? I think everyone knows that the radius of convergence is infinity. The domain is all real numbers. Every single x value converges to e to the x. So that's a pretty powerful power series because we have a domain of all real numbers. That's not always going to happen, but sometimes it does. All right, a few more examples here. This time we're given the series. We don't have to figure out what the series is. We also don't necessarily know what this series converges to, but we aren't asked to find that. We're asked to find the radius of convergence. So this is just the ratio test. The ratio test, once again, is, ratio test, once again, is that we take the limit as n approaches infinity of the ratio a sub n plus 1 divided by a sub n. And we don't have to worry about the alternating nature of this. This part right here can get thrown away because of the absolute value. So we're just going to look at x minus 5 raised to the n plus 1. I'm going to replace all of the n's with n plus 1's. So it's n plus 1 times 2 raised to the n plus 1. And divided by the nth term. So I'm going to put the n times the 2 to the n on the top, and the x minus 5 to the n on the bottom, and reduce what you can. When we reduce what we can, we've got an x minus 5 on the top, we've got an n on the top, we've got an n plus 1 on the bottom, and we've got a 2 on the bottom. Now again, x is not a variable in this limit. N is the only thing that's happening here. So we can actually, if we wanted to, if this helps, we can factor out the x minus 5 over 2. That part doesn't have anything to do with the limit. The only thing that we're taking the limit of is the stuff with n in it, and that might help clean up the expression a little bit so we can see what happens. And when we look at this limit, it should be clear that that limit equals 1. So 1 times the absolute value of x minus 5 over 2. Now remember that the ratio test asks us to determine when we are going to get a value that is less than 1. If we get something less than 1, then we know that that the series is going to converge, right? So we have to now we're ready to pick x values that cause this fraction to be less than 1. So absolute value inequalities, we know that this thing has to be between -1 and +1. So multiply both sides by 2. We'll add 5 to both sides. And we get the interval of convergence. The interval of convergence, the IOC, is 3 to 8. Now we don't know what happens at 3 and at 8. Those are the endpoints. We have to now check the endpoints to determine what happens there. But we definitely know that the radius of convergence is, well, what is the radius of convergence? We might want to look at a number line here, and we can see that 3 and 8 are endpoints, and exactly in the middle is 11 halves. So we've got, let's see, I guess 5 halves, right? The radius of convergence is 2.5. The radius of convergence is 2.5. All right, and you might notice the 5 and the 2. Those are what are determining that radius of convergence. So we're not quite done yet. We have to now check the endpoints. We're going to say we're going to ask the question, does this series converge when x equals 3? So we'll look at negative 1 raised to the n plus 1 times, let's see, x minus 5 is going to be 3 minus 5, so that's going to be negative 2 raised to the n divided by n times 2 to the n. Okay, so we replace all of the x's with 3's, and we're asking the question, does this series converge? Well, let's take a look. The exponential negative 2 to the n is actually going to be rewritten as negative 1 to the n and also 2 to the n. That's going to make things a little cleaner for us because then we can cancel out the 2 to the n's here. And let's see what else we can do. We can say that the negative 1's here, we've got a negative 1 to the n plus 1 and a negative 1 to the n. We can add those exponents and get 2n plus 1 for the exponent of the negative 1. And as we look at this, we're going to hopefully recognize this as perhaps it's an alternating harmonic series. But when in doubt, expand it out, and let's see what happens. We're going to start with n equals 1, and n equals 1 is going to give us, let's see, our exponent is going to be 2 plus 1 is 3, so it'll be negative 1 over, over 1. And when n equals 2, we're going to get 2 times 2 plus 1, which is 5. So that's actually going to be negative 1 to the 5, which is also negative. So because of this crafty little 2 right here, we're actually not alternating because all of our exponents for the negative 1 are odd. So this thing is actually a divergent by p-series, diverges. What does that mean? Well, it means I can't spell. Diverges means that we do not include 3 as part of our domain. 3 causes the series to diverge. So we're almost done, I promise. The next part we're going to have to do is we're going to have to check to see if the other endpoint of 8 is going to cause us to converge or diverge. And the only difference here is instead of a negative 2 inside here, we're going to plug in an 8 in for x. We're going to get 8. That shouldn't be 8, should it? Wow, let's back up a sec. This should be 7 because 5 plus 2 is not 8. 5 plus 2 is 7. I thought it was a little strange to have that fractional radius of convergence. All right, you guys were shouting at your screens, weren't you? So that's going to change all of this stuff. I thought it should be 5. All right, so 5 is the center, so 2 is the radius of convergence. Sorry for the confusion there, folks. All right, but yeah, when we plug in 7 into here, we get 7 minus 5, which is positive 2. And then we have also the n times 2 to the n down on the bottom. And just like we saw before, the 2 to the n's cancel out, but we don't have that extra bit right here that we used to have, right? That part right there, that extra alternating piece, is not part of this problem. So when we simplify this down, we look at negative 1 to the n plus 1 over n, which converges. We know this converges conditionally because it's the alternating harmonic. All right, so that means if it converges, then we want to include that. All right, so and then we're going to include everything in between the endpoints from 3 to 7. From 3 to 7 is all included. So the interval of convergence, actually, I'm going to have to change this interval over here. So instead of not including the 7, I'm going to include the 7. And these would be some of the questions that I could ask. And notice that we can do the ratio test to find the endpoints, but then we have to do 2 different tests, one for each of the 2 endpoints.